Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module, we are discussing ionization energy and electron affinity. In this module, we are discussing about ionization energy, factors influencing ionization energy, periodic trends in ionization energy, electron affinity or EA, factors influencing electron affinity, periodic trends in electron affinity, and problems based on these concepts. First of all, we are discussing about ionization energy. You previously heard about the definition of ionization energy, and you are recalling the concept that ionization energy is a periodic property. A periodic property is a property which depends on the position of the element in the periodic table. Now we can have a detailed discussion on ionization energy. First of all, definition of ionization energy. Ionization energy or ionization enthalpy is defined as the amount of energy required to remove the most loosely bound electron from an isolated gaseous atom to form a cation. You have to keep this important point in your mind. That is, it is the energy required to remove an electron from isolated gaseous atom. What is the significance of isolated gaseous atom? In keeping the definition of ionization energy, we have to maintain this point. Isolated means it is totally free from all kind of interaction. Isolated gaseous atom is an atom in the gaseous state which is totally free from all kind of interactions. Therefore, in order to remove the interference of all other energy terms, we are fixing isolated gaseous atom to define ionization energy. This is the pictorial representation of ionization energy concept. Here at the center portion there is an atom with the surrounding electrons. Electrons are revolving around the nucleus, and when a particular amount of energy is donated to that atom, electrons will expel from the outer shell. That energy required is termed as ionization energy. Typically, this ionization energy values are measured in units of electron volt or kilojoules per mole. So, electron volt and kilojoule per mole are two convenient units of ionization energy. 1 electron volt equal to 1.602 into 10 raised to minus 19 joule, and joule is the SI system of energy. And for convenience, ionization energy can be represented in small unit like electron volt or in higher unit like kilojoule per mole. Ionization energy is a key indicator of an atom's reactivity and its tendency to form chemical bond. This simply implies that ionization energy has some close relation with the tendency of an atom to form some chemical bonds. The first ionization energy, abbreviated as IE1, is the energy required to remove an electron from a neutral atom, or it is the amount of energy required to remove the first electron. In a similar way, we can define second ionization energy, third ionization energy, etc. What about second ionization energy? The second ionization energy, abbreviated as IE2, is the energy required to remove a second electron after the first electron has already been removed. Suppose you are having a sodium atom and I am removing the first electron to get Na plus. So, one electron is removed from here. The energy required for this purpose is called first ionization energy of sodium. Suppose I am removing one more electron from this Na plus, then the second ionization energy can be expressed like this: Na plus on further removal of one more electron just converted to Na2 plus and 1 electron. The energy described by this equation is ionization energy second or second ionization energy or IE2. IE2. This one represents the first ionization energy or IE1. So, we can have a third ionization energy and higher ionization energies also. So, what about IE3? Third ionization energy means you are going to again remove one more electron from divalent cation. The energy required is called third ionization energy. Now, these first ionization energy IE1, IE2 and IE3 are the first, second and third ionization energies, and these are energies to remove electron from a neutral atom, a monovalent and a divalent cation respectively. This is the equation corresponds to first, second and third ionization energy in its general form. Here X is an element, X is present in gaseous state and we have to consider X as isolated gaseous atom. On providing IE1, X is converted to X plus gas. X plus gas is converted to X2 plus gas on providing second ionization energy, that is IE2. On providing third ionization energy, that is IE3, X2 plus gas is converted to X3 plus gas. On comparison, we can arrive at the conclusion that IE1 less than IE2 less than IE3. What is the reason for this gradation? We can connect it to the effective nuclear charge. In the first case, you are removing an electron from a neutral atom. Their electronic charge and nuclear charge are equal and opposite. In case of second ionization energy, you are removing an electron from a cation, which is associated with more nuclear charge compared to electronic charge. As the nuclear charge is high, size is small, and the interaction between electron and nucleus will be high, so you have to provide more energy. So, the magnitude of second ionization energy definitely higher when compared with the first ionization energy. In a similar way, third ionization energy is higher than second ionization energy. So, in general, ionization energy follows this regular pattern, IE1 less than, IE2 less than, IE3, so on so. Now, we are discussing factors influencing ionization energy or ionization enthalpy. What are important factors that govern the magnitude of ionization energy? So many factors like nuclear charge, size of atom, electropositivity, electronegativity, etc. has some close connection with the ionization energy. Let us analyze each and every factors that govern ionization energy. The first factor is atomic size. Ionization energy decreases with the increase in atomic size. Atomic size can be expressed in terms of atomic radius, such as covalent radius, van der Waals radius, etc. With increase in size, you can see a decrease in ionization energy or ionization enthalpy. As the distance between the outermost electron and the nucleus increases, the force of attraction between the valence electron and the nucleus decreases, such that you can easily remove the outermost electron by providing small quantity of energy. It is clear that ionization enthalpy or ionization energy inversely proportional to atomic size. Moving on to the next factor, that is nuclear charge. How nuclear charge influences ionization energy? The ionization energy increases with increase in nuclear charge. This is due to the fact that with increase in nuclear charge, with increase in positive charge, the electron of the outermost shell are more firmly held by the nucleus. That is, the distance between nucleus and the electron decreases. That means the electron under our consideration is under strong control of the nucleus, and hence it is very tough to remove. That means you have to provide high energy, which implies that the situation leads to high ionization energy. So we can conclude like this: ionization enthalpy or ionization energy is directly related to nuclear charge. Now the third factor is shielding or screening effect. The electrons in the inner shell act as a shield or screen between nucleus and the electrons in the outermost shell. Such an effect is called shielding effect. Shielding effect has some effect on ionization enthalpy. And the larger the number of electrons in the inner shell, greater is the screening effect. So, higher screening effect lowers ionization energy. Penetration effect of the electron is another influential factor of ionization enthalpy. The ionization energy also depends on the type of electron which is removed. An electron, an s electron, penetrates more close to the nucleus and is therefore more tightly held than a p electron. This simply implies that it is difficult to remove an s electron compared to a p electron. That is, if you are ionizing an s electron, energy required will be high than ionization of a p electron. If other factors such as nuclear charge, etc. keeping constant, then we can say ionization energies follows the order S greater than, P greater than, D greater than F. This is the order of the penetration effect. S electrons are more close to the nucleus and F electrons are away from the nucleus. That is, S electrons are deeply in attraction with the nucleus and it is tough to remove an electron from an s orbital compared to p, d or f orbitals. Now, another factor that governs ionization enthalpy is the electronic configuration. You are familiar with the stable and unstable electronic configurations. The extra stability associated with the noble gas, the inertness of noble gas is attributed to their stable electronic configuration. If an element is present in its stable electronic arrangement, then we have to provide more energy to remove the electron. That is, if electronic configuration is stable, ionization energy will be high. If an atom has exactly half-filled or completely filled orbitals, then such an arrangement has extra stability. The removal of an electron from such an atom requires more energy than what we expect. That is, more stable the electronic arrangement, higher will be the ionization energy. Now, we are discussing periodic trends in ionization energy. You know about the term periodic trends. Periodic trends means certain properties like ionization enthalpy, electron affinity, electronegativity, etc. varies as we proceed through a group or through a period. If we move from top to bottom in a group, we can see some tendency, and in many cases that tendency is exactly opposite to the proceeding across a period. That is, if we move from top to bottom in a group, the properties are opposite as we move from left to right along a period. And in this part, we are discussing the variation of ionization energy along a period and along a group. First of all, variation of ionization energy across a period. In a period, we are migrating from left position to right position. And as we proceed from left to right across a period, you can see that ionization energy increases. This ionization energy increase is due to increase in nuclear charge and small atomic radius. Some exceptions may occur with elements having stable half-filled or full-filled subshells. For example, nitrogen versus oxygen. In the case of nitrogen and oxygen, as we proceed from left to right, we are expecting that the ionization energy of oxygen must be greater than that of nitrogen. But here there is some anomaly. The anomaly arises due to stable electronic configuration of nitrogen. And now let us take the electronic arrangement of nitrogen and oxygen. You know, oxygen has an electronic configuration 1s2, 2s2, 2p4. Whereas nitrogen atom has an electronic configuration 1s2, 2s2, 2p3. This 2p3 arrangement is a stable electronic arrangement since it is half-filled configuration. However, in the case of oxygen, the electronic arrangement of outermost shell is not half-filled, or it is a 2p4 arrangement. When comparing these two elements, it is very well clear that nitrogen is associated with some stable configuration, and hence definitely the ionization enthalpy of nitrogen is greater than that of oxygen. But based on the normal periodic trend, we are expecting that oxygen is having higher ionization enthalpy than nitrogen. But in actual practice, nitrogen is associated with high ionization energy compared with oxygen. This is due to stable electronic arrangement of nitrogen compared to oxygen. So, if we are ignoring such stable electronic arrangement, the normal trend is as we move from left to right, there is an increase in ionization energy. This is due to increase in nuclear charge. Now we are discussing the trend in ionization energy along a group. In a group, if we proceed from top to bottom, we can see some variations in ionization energy. Definitely, there is a decrease in ionization energy as we move from top to bottom. And this ionization energy decrease is attributed to increase in atomic size as well as the shielding effect associated with the system. So, if we proceed from top to bottom along a group, there is an increase in size and a decrease in ionization energy. This picture illustrates the general, regular, periodic trends in ionization energy. First part is left to right along a period. If we proceed from left to right along a period, ionization potential or ionization energy generally increases. If we move from top to bottom in a group, ionization potential or ionization enthalpy or ionization energy generally decreases. This about the periodic trends in ionization energy. First, ionization energy values of S and P block elements. This picture gives the first ionization potential values, and this is the periodic arrangement. This periodic arrangement exclude D and F block elements, and for convenience we are showing the ionization potential or ionization energy values of some S and P block elements. Some exceptions are noted. The exceptions are due to the fact that there may be stable electronic arrangement, and the elements shown in red, that is helium as well as neon, they are associated with very high ionization energy values. Their very high ionization energy values is attributed to their highly stable electronic configuration and small size. So, in the periodic table, ionization energy shows some gradual variations along a period as well as along a group. Some additional factors also govern the magnitude of ionization energy. Now, in the periodic table, the ionization potential follows some very systematic trends. This is the consolidation of some observations as far as ionization energy, as far as the periodic table of elements are concerned. Maximum ionization potential in any period is shown by inert gases. So, if you are taking a particular period, the element with the highest ionization potential in that period will be an inert gas or a noble gas. For example, In the first period, it is helium. In the second period, it is neon, so on and so. Maximum ionization potential is shown by inert gas. At the same time, the minimum value of ionization potential is shown by alkali metals. For example, if we are taking the second period, the highest ionization energy is shown by neon. At the same time, lowest ionization energy is given by lithium, since lithium is an alkali metal. So, in a particular period, least value of ionization energy or minimum value is shown by alkali metals and maximum value is shown by inert gas. Maximum ionization energy in the periodic table is reported in the case of helium. Helium is the element with the highest ionization energy. Minimum ionization potential in the periodic table is for cesium element, which is a alkali metal and it is having highest size, and cesium is associated with the minimum ionization potential. So, these are four important consolidations as far as ionization energy of all the elements in the periodic table are concerned. Now, we are discussing another important periodic property of this module, that is electron affinity, which is abbreviated as EA. Electron affinity is defined as the amount of energy released, sometimes absorbed, when an atom gains an electron to form an anion. That is, an isolated gaseous atom is having an one more electron to convert it into an anion. The energy change. In many cases, energy is released, but in very rare case, energy may be absorbed. That energy change is taken as electron affinity. So, this is the expression for electron affinity. X is an isolated gaseous atom. It adds an electron to convert it to X minus anion, which is again in the gaseous state. The energy term delta E is nothing but electron affinity or electron gain enthalpy. And this is the pictorial illustration of electron gain enthalpy. A is a neutral atom in the gaseous state. One electron is shown here, which is added to A, and A is converted to A minus. You can see the increase in size. When an electron is added to an atom, it is converted to an anion, and the size of anion is greater than that of atom. So, A minus is produced and there occur some energy changes. The associated energy changes is taken as electron affinity. Now, for most non-metals, energy is released when an electron is added as the nucleus attracts incoming electron. The electron affinity is negative in such a case. For example, the electron affinity of fluorine and electron affinity of chlorine are negative values. Electron affinity is also expressed as electron gain enthalpy. For some atoms like noble gases or some metals, metals are electropositive, they do not want electrons. Noble gases are already in a stable electronic configuration. In such cases, energy must be supplied to add an electron due to their stable electronic configuration or repulsive forces. In such a case, we have to provide some energy, or we can say that electron affinity is positive in such cases. Electron affinity indicates the tendency of an atom to gain electrons. Now, factors influencing electron affinity. Various factors are describing here. First factor is atomic size. As atomic size increases, the distance between the nucleus and the added electron also increases. And this increase in distance weakens the attractive force between nucleus and the incoming electron. That results in less negative electron affinity, or we can say that the amount of energy liberated will be very small. So, as the size increases, magnitude of electron affinity decreases. This is an example which illustrates the point. Chlorine has an electron affinity of minus 349 kilojoule per mole, and bromine is having a value minus 324 kilojoule per mole. Here bromine is bigger in size when compared with the chlorine. So, as size increases, electron affinity decreases. Next factor that governs electron affinity is the nuclear charge. A higher nuclear charge increases the attraction between nucleus and the extra electron added. This leads to more negative electron affinity. That is, we can say nuclear charge is proportional to electron affinity. For example, electron affinity of oxygen is minus 141 kilojoule per mole, and that of sulfur is minus 200 kilojoule per mole. Electronic configuration is another factor that influences electron affinity. An atom with a stable electronic configuration, full-filled or half-filled arrangements, have less tendency to attract electron. In such a case, the magnitude of electron affinity will be very low or even positive. For such atoms, electron affinity is either less, negative or even positive. If you are considering a noble gas atom, what will happen is they are associated with the positive value of electron affinity. Here we are taking nitrogen as an example, which is associated with a stable electronic configuration of 2p3. When an electron is added, the stability may be disturbed, so it is associated with a positive value of electron affinity, which is equal to 7 kilojoule per mole. Shielding effect is another factor that governs electron affinity. Greater the shielding effect, it reduces the effective nuclear charge experienced by the added electron, making electron affinity less negative. This is an example. If in fluorine, shielding is minimal because it has fewer inner electrons, and electron affinity is minus 328 kilojoule per mole. Electron-electron repulsion is a very important factor that governs electron affinity. When an additional electron is added to an atom, it may repel the electrons which are already present in the same energy level. Such a repulsion is termed as electron-electron repulsion, and electron-electron repulsion can reduce the stability of the added electron, making electron affinity less negative. And the electron affinity of chlorine is minus 349 kilojoule per mole, which is greater than fluorine, which is minus 328 kilojoule per mole. This is a very important exam point of view. This part is very, very important. The electron affinity of chlorine is greater than that of fluorine, and this is attributed to high interelectronic repulsion in fluorine compared to chlorine. So, chlorine is having high electron affinity. Discussing periodic trends in electron affinity. Across a period, we can say that electron affinity become more negative as you move from left to right along the period. This is due to decrease in atomic size and increase in nuclear charge. These are some examples. Lithium, carbon and fluorine are the elements present in the same period. Their associated electron affinity values are shown here. You can see there is an increase from left to right across a period. Second one is the periodic trend along a group. As we move from top to down in a group, electron affinity becomes less negative due to increase in atomic size and greater shielding effect. This about the examples for illustration. Chlorine is associated with a value of minus 349 kilojoule per mole. Bromine is having minus 324 kilojoule per mole, whereas iodine is associated with an electron affinity value of minus 295 kilojoule per mole. Now, some problems based on the concept we have discussed, that is ionization energy as well as electron gain enthalpy or electron affinity. This is the first MCQ. Which element has highest first ionization energy? These are the options: sodium, potassium, helium and oxygen. In order to arrive at a final answer, we have to check on the size as well as electronic configuration. On careful analysis of these four options, we can arrive at the final answer as C, that is nothing but helium. You know, helium is the element in the periodic table which is associated with the highest ionization energy, and this is because of the fact that it is a small size as well as more stable electronic configuration. This is the second question. Why the second ionization energy of magnesium significantly higher than first? An increase in nuclear charge, shielding effect increases, stable electronic configuration of Mg+, electron is far away from the nucleus. This is the answer to this question. Answer is option A, increase in nuclear charge. Calculate the energy required to remove 2 moles of electrons from sodium atom. Given that the first ionization energy of sodium is 495.8 kilojoule per mole. These are the options, and you can calculate the answer like this. For removing the first electron, 1 electron per mole, you have to provide 495.8 kilojoule. For 2 moles, you have to multiply this 495.8 kilojoule with 2, and the total energy required will be 991.6 kilojoule, and your answer is option B. Which of the following elements has the lowest first ionization energy? Fluorine, oxygen, lithium and potassium are the options. You have to think the answer based on electronic configuration and size. Potassium is associated with the bigger size, and only one electron is present in the outer shell. It is a metal. It is associated with the lowest value of first ionization energy. So your answer is option D, potassium. And why does ionization energy increases across a period? These are the options. On careful analysis of the options, we can analyze the result as answers option C, that is nuclear charge increases. Chlorine releases 349 kilojoule per mole of energy when it gains an electron. How much energy will be released when 0.5 moles of chlorine atom converted to Cl- ions? This is for 1 mole, and the question is about 0.5 mole. These are the values. You can calculate the answer like this. 349 kilojoule per mole is for 1 mole, and in the question they are asked for 0.5 mole. So you have to multiply with the 0.5, that is 1 by 2. So the result is 174.5 kilojoule. Why is the electron affinity of nitrogen less negative than that of oxygen? These are the options, and the answer is very clear. Nitrogen has stable half-filled electronic arrangement of 2p3 when compared with the oxygen, which is having an arrangement 2p4. And the last question is a match the following type of problem. In the first column, there are some electron affinity values, electron affinity of some elements, and in the column B, there are some numerical values of electron affinity, and you have to make a match between these values. In the first column, electron affinity of fluorine is there, chlorine, bromine and iodine is there. It is very well clear that these all are halogens. Chlorine is having highest value, then fluorine, then bromine, and final least value is for iodine. So your answer is answer 1B, 2A, 3C and 4D. That all about the present module. Have a nice learning experience. Thank you.